Okay, so in this video, we're going to be looking at geometric interpretations of solutions of planes in 3 dimensions. So there are a couple of different ways that your 3-dimensional planes can look. Now, the first one is the most common, which is when you have a unique solution. And that is kind of like if you picture the corner of a room. You've got where the floor meets the 2 walls, and in that one spot where all things are touching, that is the one unique solution. So that's our most common way of looking at these, which you see you've got you've got our identity matrix, and then you've got A, B, C here. The other way that it can be represented is if you have 0 solutions. So you'll see for this system we have 0 solutions, this one. And for this system, we've got 0 solutions. And for this system, we've got 0 solutions. Now, the only difference between these two is that if the 2 planes are distinct with parallel normals, the 3rd plane is not parallel. And for this one, the normals are not parallel. So their matrices look the same. But if you scroll up for this one here, you can see that if you've got 3 planes that are all at the same angle, they are going to have a matrix that looks like that. If you've got infinitely many solutions, it means that instead of having one point where they all touch, you're going to end up with an equation of a line where they all touch, because along this line here, they are all touching. Now, that will give you a system that looks like this. You'll notice that we've got a 0 in that position instead of a C value. So that's how you can identify that it's going to be infinitely many solutions. The other way, the last option that we look at, is when you've got 3 planes on top of each other. So if you've got 3 on top of each other, it will appear like this. So we're going to now test a couple of different matrices to see which one it aligns to when we're talking about its geometric interpretation. So this is question 12 from the textbook. Determine the number of possible solutions by examining the normal vectors algebraically. Convert the equation to an augmented matrix and use technology to solve the system, and then we're going to describe how that solution can be interpreted geometrically. Now, for part I, all we need to do is we need to determine what is the determinant of our matrix that we're going to be calling A. So, if you look back over here, you'll see that here, this one will not be equal to 0. Maybe we won't do that part. Okay, we're just going to go straight into testing our matrices. All right, so now first thing I'm going to do is I'm going to go Option, Matrix, go across so that I can get row reduced echelon form. And then I'm going to go back here to Math, Matrix, input my order as 3 and 4 because I'm going to input the augmented matrix. So that's going to be 5, 8, 1, -5, -7, -4, -5, -11, -3, -1, -6, and 4. I press enter, and you'll see that I get a row of 1s, or our identity matrix on this side, and a 6, a -4, and a -3. So the way that I can describe A, because it appears like this matrix here, I can say that this has one unique solution. Okay, B. Do the same thing again. We're going to input it. Okay, so -7, 7, 42, 9, 5, -2, 8, -11, 7, -4, -4, and 2. Enter. Okay, so this is one of the more interesting scenarios. So we've ended up with a 1, and a 0 here, meaning that this isn't a true statement. So let's go over and look at our matrices to see which one fits this form. So even though I've got zeros in these positions, they can still act like A or B. Okay, it's more what's happening in this cell down here. So we can see that it's either going to fit the form of this one here, or it could fit the form of this one down here. Now, the way that I'm going to determine which of those it matches is I'm going to be looking for whether or not two of the planes are parallel. Now, what that is a fancy way of saying is I'm going to rearrange all three equations into the form of one of the letters is equal to the rest of it and see if one can be scaled. Now, we don't care what the coefficient is, because if the we don't care what the constant is, because if the constant is different, that just shifts it up or down in the graph. We want to make sure that we've got the same thing in front of x, the same thing in front of y, and the same thing in front of z. So let's do that now. Negative 7x plus 7y plus 42z is equal to 9. Move this to the other side and move this to the other side, and I'll end up with negative 7x is equal to 9 minus 7y minus 42z, and then I'll take this 7 to the other side by dividing everything by negative 7. Okay, now we're going to do the next equation. 5x minus 2y plus 8z is equal to negative 11. Take this to the other side, take this to the other side. I'll be left with 5x is equal to negative 11. Well, that was a plus before. No, it wasn't. It was a minus. So now it's going to become a plus 2y minus 8z. And then I'm going to divide the whole thing by 5. Okay, so now that's going to leave me with, so far if I look at the coefficient just in front of y, negative 7 divided by negative 7 is a 1. 2 over 5 is a fraction. They're not the same. So far I can say that they're not the same. It hasn't showed me so far that it's going to be matching with the one where they're parallel. Okay, so let's try the last one. 7x minus 4y minus 4z is equal to 2. Take this to the other side, take this across. I'll be left with 7x is equal to 2 plus 4y plus 4z, all divided by 7, because I'll take that across. And now I can see 4 over 7 is not going to be the same as it is in this case, and it's not the same as it is here. Now, if I look at the z's, that simplifies to 6. That will simplify to a fraction, and that will be a different fraction as well. So none of these things are parallel. I would have expected that if they were like this one, they would be in the same direction, meaning that the values in front of y and z should have been the same. The constant could have been anything, but the values in front of z and y need to be the same. So this one is this. The normals are not parallel. So that's the conclusion I can draw for B. The normals are not parallel. Okay, and that's where we'll stop now.